Welcome to today's webinar. The topic today is fire design in steel structures with Rfem 6. My name is Andreas Hörold. I'm responsible for marketing and PR in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, etc. I will be the moderator today and I will answer your questions together with Niklas Wanke. The presentation will be done by Dr. Jonas Bien. My two colleagues are the responsible persons of the steel design add-on, and they also work in the customer support. And please enjoy today's webinar. I see something how you can ask questions. First, I switch off my webcam that you can see the full screen. Just press the button with the question mark, then enter your question in that field, press send, and we will receive your question. And we will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's at the moment all from my side. I hand over to Jonas. Jonas, it's your turn.
All right, thanks Andreas for the introduction. I would also like to welcome you to the webinar. Thanks for being with us today. The topic of fire protection in steel construction has never been covered in detail in a Dlubal webinar before, although we notice a high and constant interest in this subject from our user base. To finally close this gap, I will spend quite some time on the theory and present the basic assumptions of the solution that we implemented in our programs. I would then like to jump into Rfem to show you how we can activate the fire protection checks in the steel design add-on and which settings we need to adjust. We will then check the fire design results together and discuss the effectiveness of various fire protection measures. We will do all this in the context of a very simple example so we can focus on the core ideas. Finally, I would like to touch some advanced topics and questions that come up when confronted with the fire design of an entire structure. When talking about fire protection in general, we need to discuss to what extent does it affect the structural engineer and what are the requirements to be met. Before we can define fire protection measures and requirements, the objective of fire protection must be clear. The fire protection objective is usually specified in the respective building regulation. As an example, I looked up the German building regulation and it states that buildings must be designed in such a way that the development of a fire and the spread of fire and smoke is prevented and that people and animals can be rescued and effective extinguishing work can be carried out in the event of a fire. Based on the fire protection goal, protection measures can be defined. In the literature, those measures are usually categorized into technical, structural, and organizational fire protection measures. Our job as civil engineer is to plan and implement the structural fire protection measures. One of those involves verifying sufficient fire resistance of structural elements. The effectiveness of this measure in relation to the protection objective is obvious. The greater the fire resistance of the structure, the more time users have to evacuate the burning building, or the harder it is for the fire to spread to other buildings. The fire protection measure is further specified in the building regulations. In the German building regulations, for example, those requirements are defined depending on the building class and the function of the structural element within the building. For example, certain building components must be fire retardant. This classification may seem a bit unspecific at first glance, but it is linked to clearly defined resistance classes given in EN 13501 Part 2. Those resistance classes are described using a sequence of letters and numerical value. The number indicates how long a component must be able to withstand fire, while the sequence of letters specifies what function the component must fulfill over this time. The letter R stands for the load bearing capacity. For a component with an R30 requirement, the load bearing capacity must be verified for 30 minutes in the event of a fire. This verification can either be test-based or calculated using the Eurocodes. The latter will be the topic of today's webinar. So let's take a look at how fire design is regulated in the Eurocodes. I would like to start with the combinatorics. According to Eurocode 0 or EN 1990, the case of fire is to be regarded as an exceptional design situation. Accordingly, the mechanical actions are combined without partial safety factor. The use of C to 1 is recommended in the main document for the leading variable action, but there are many deviations in national annexes. In Germany, for example, C11 is prescribed for leading wind actions. It is obvious that the combination rule results in significantly lower actions when compared with the permanent and transient design situation that we commonly use for the design under normal temperature. As a safe side assumption, the loads from the code design multiplied by a reduction coefficient can also be used. However, this is generally uneconomical and therefore not recommended, especially when we use a design software that can do the correct combinations anyway, like Rfem. In addition to the mechanical actions, the thermal action in accordance with EN 1991 Part 1.2 must also be taken into account. In the event of a fire, there's a considerable increase in the ambient temperature, and sooner or later, the structural elements exposed to the fire will heat up as well. This has a dramatic effect on the material properties of steel components on one hand. On the other hand, the temperature increase can lead to indirect stresses in case thermal expansion is restrained. Real fire scenarios develop in 4 stages. We have the incipient stage, the growth stage, the fully developed fire phase, and the decay phase. The transition to the full fire phase is called flashover and is associated with a rapid rise in temperature. For engineers, it is very challenging to accurately predict the development of a natural fire scenario. Instead of trying, so-called nominal fire curves have been established almost 100 years ago to describe the temperature developed in a compartment over the duration of the fire in a simplified manner. The standard temperature curve is used for fires inside buildings. This temperature curve is also used for standardized fire tests on structural elements, which means that the behavior of typical elements under this nominal fire exposure is quite well documented and verified. Alternatively, the Eurocode also allows the use of more sophisticated approaches to predict the temperature development, such as parametric fire curves, zone models, or results from CFD analysis. The actual design of structural elements is regulated in the respective material-specific Eurocode, such as the Eurocode 3 Part 1.2 for steel construction. In principle, all ECs or Eurocodes distinguish between 3 alternative methods with increasing complexity and accuracy. The simplest design approach is design by tabulated data. This is oftentimes used for fire design of concrete elements, where it is sufficient to choose the suitable dimensions, for example, wall thickness, for a specific fire class. This approach is unfortunately not available for steel structures. In the second level, we find the so-called simplified design methods. Here, the thermal actions are prescribed by nominal fire conditions, such as the standard temperature curve for fires inside of buildings. For such conditions, Eurocode 3 Part 1.2 gives clear rules for the design of steel members. This verification can either be done based on the resistance or based on the critical temperature. The most accurate but also complex analyses are possible under the advanced design methods. The thermal actions are usually derived by more sophisticated methods here, such as parametric fire curves, zone models, or CFD. This enables a more economic design most of the times. The design rules are very openly formulated. Any suitable thermal and mechanical analysis model can be employed. However, the validity of the chosen approach must be proven on a case-specific basis and requires a high level of expertise. In Rfem 6 and also RStab 9, the resistance-based simplified design method is implemented. A system calculation under elevated temperatures is not required in this case. The design concept is very similar to the design under normal temperatures, but under reduced load as we combine actions in the exceptional design situation. The thermal action is only taken into account on the resistance side and induces a reduction of design-relevant material properties. I would like to explain this point more detailed in the next slides. As explained on the previous slide, the simplified design method is linked to the application of the standard temperature curve. This means the development of the ambient temperature during a fire is approximated in a simplified manner according to the logarithmic function shown here. The standard temperature curve idealizes the full fire phase and neglects the growth and decay phase of the fire. So the development of the ambient temperature is specified by the standard temperature curve. However, for design purposes, we are interested in the actual temperature of the structural member. According to EN1 or Eurocode 1, Part 1.2, two different components must be taken into account when analyzing the transport of heat from the surrounding hot air into the heated component. The heat flux from convection, so the exchange of heat from the hot ambient air and the cold component surface in the boundary layer, and the heat flux from radiation or thermal radiation. Additionally, Eurocode 3, Part 1.2 contains a formula for calculating the temperature development of unprotected steel members. In addition to other parameters, this formula includes the aforementioned net heat flux. The given formula assumes a uniform heating of the cross-section and a sum of the input variables shown here change with the component temperature. It can only be solved iteratively in small time steps described by delta t. I know there's a lot to explain, but I would like to leave the formula as it is right now. We will come back to the various parameters in detail later, as they are important influencing variables for fire design and any fire protection measures. For now, we take note that we can describe the relationship between ambient temperature and component temperature in the event of a fire. But how does the member temperature actually affect the design? According to Eurocode 3 Part 1.2, design-relevant material parameters such as the yield strength and stiffness must be reduced depending on the material temperature, while the yield stress only has to be reduced at temperatures above 400 degrees Celsius, but then quite rapidly, as you can see here. The stiffness already decreases at significantly lower component temperatures. At a temperature of around 600 degrees Celsius, the reduction of the yield stress is already does already account for 50% roughly. At 800 degrees Celsius, it is almost 90%, so there's only very limited resistance left. These reduction factors are then considered in the member design equations under fire conditions, which are otherwise very similar to the verifications we use for the design at room temperature according to Eurocode 3 Part 1.1. But before we drown in theoretical content, let us jump to Rfem and go through the design steps in a small example. Okay, so I have already prepared this simple model beforehand. So it's just a simple beam with an intermediate support in lateral direction in the middle. It's an HEA 300 section and 10 meter long. I think the steel is S235. Yes. This member is already loaded by 3 load cases, so self weight of the beam itself. Then we have dead load, an additional of 5 kilonewton per meter, and load case 3 is imposed load category B with 7.5 meter per kilonewton per meter. I've also defined one design situation for the code design of this member. So the usual combination permanent and transient, as you can see here, and this results then into automatically generated load combinations. I want to start with the code design. So I switch on the Steel Design add-on, go to standards, and for now I will just use the main documents of the Eurocodes and use the common rules. Okay, and as we are used to, the design add-on has already recognized that we have this member that can be designed with our Steel Design add-on. So that's fine. And besides the section checks, I also want to do the check for lateral torsional buckling according to the equivalent member method. So I will also define an effective length. And I want to leverage the intermediate node. So I will just enter or assign a lateral support here at the middle, as we have modeled it in the global model as well. Okay, so let's do this. And by the way, this assignment of the buckling length is valid for the code design and also for the later fire design that we are doing. Okay, but for now, let's start with a code design, the usual thing that we know. I will just run the simulation now, this very simple case, and we will check the utilizations that we get under normal temperature. Okay, so as we are used to, we get section checks for shear and bending. There's also, I think, shear buckling. And since we also activated the buckling length, we also get the stability check for lateral torsional buckling. We can see that the maximum utilization is around 83%. So this is completely fine. Everything's good so far. So now let's see how this changes when we investigate the fire scenario. So let us do all the adjustments that we need to take in order to activate this. First of all, we need a design situation that is appropriate for our fire case. So I will add a second design situation for the accidental load case using psi-to-1 as it is prescribed in the main documents of the Eurocode. We can again check the combination rule, and this is totally fine for us and looks like the rules or the rule that I showed you before in the slides. Okay, so I get two additional load combinations now for the fire situation. And before what we can then also check, because it already directly pointed me to this thing, is under Steel Design input data. I also want to make sure that this newly created design situation for the accidental situation is matched with the correct verification scheme. So for these load cases that are defined now under design situation 2, I want to do my fire design checks, and the Steel Design add-on has already recognized that, so it matched the design situation of the type accidental with the verification checks for fire situation. We have to be a bit careful if we want to investigate other accidental actions such as impact or explosion or something like this. Then we would need to turn this around and do a different setting here, because in that case we wouldn't be interested in the fire design checks to be done from the Steel Design. Okay, then we also have to define some additional settings for the fire resistance design checks. So as you can see here under design configurations that we can assess, for example, directly through the member, we can see that we have, besides the ultimate configuration for the ULS checks and the serviceability configuration for the SLS checks, we also, for all codes that support the fire design, we have these fire resistance configuration. And in here, we have to, first of all, define what the resistance class of my member is going to be. So at what time I want to perform my fire design checks. In this case, I would assume that my member needs to survive for 30 minutes, so or has an R30 requirement. So I will set 30 minutes as the required time for the fire resistance. We can also see that here under the temperature curve for determination, we have by default set the standard temperature time curve, and this is the one that we want to use for internal fires and the member design method here. We could also give a manual material that the program then takes to perform the fire design checks, but we want to have the temperature of the steel defined by the standard temperature time curve here. And we want to do the check after 30 minutes. The remaining parameters I will not touch yet. We will come back to this later. So I will just assign this by clicking OK, and then I will run the steel design again. So we have to solve now the two additional load combinations, and then the steel design runs again. And first of all, I want to compare the forces that we now have to take for the design. So if we check the maximum bending moments for the design situation 1, so for the cold design case, we have a maximum bending moment of almost 240 kilonewton meter, while in the second design situation under accidental combination, we get more or less 100 kilonewton meters. So the load that we need to take into consideration in the hot design is much smaller than in the cold design. However, as we could already see, we now have a big problem with our design verification checks. As we can already see here, the maximum utilization is over 300%. So that's not good at all. So let's check why that is, and how comes that the utilization is so much higher than in the cold design stage. So let's actually compare some design checks. We could start with the bending check here about the strong axis. We will start with the cold design. So we are very used to this. So we have the 240 kilonewton meter design bending moment. We do the section classification. We see we have class 1 section. That means we can use the plastic design resistance here to calculate our utilization. And in this case, we have a utilization under 80%. But how does this change in the fire design situation? So let's check the respective check under increased temperature. We see we have a smaller design bending moment as already shown before. And now we already also have a different section class. That is interesting. And we can also check what is the reason for this. And this is one part where the fire design differs from the cold design, is that this material coefficient that we use for the cross-section classification is multiplied by 0.85. So it is generally all the limits for the cross-section classification are decreased by 85%. And in this case, this leads to a different cross-section classification. We have just to be aware of this. But still, for class 2 section, we can perform plastic design checks. So as you can see here in the upper right corner, plastic bending moment, design moment is calculated as in the cold design case. But then in the second step, this resistance is drastically decreased by this value ky theta. And this is actually dependent on the temperature. So we can see that under this elevated temperature, we only have 16% of our bending resistance left. This k theta is also given here in the design details as intermediate value. and it is determined by this reduction curve that I've shown earlier to you, yeah? And it depends only on the temperature of the steel at the design time. This temperature at 30 minutes that we now set as our time for the design, we can also read from the design results, and it is estimated or calculated to 760.4 degrees Celsius, while the temperature of the ambient gas, according to the standard temperature curve, is 841.8 degrees Celsius. We can also check how the development of these temperatures is over the time. So here we get a nice temperature time diagram showing the standard temperature curve here in red and the temperature of our steel member according to the formulas that I've shown you in the PowerPoint slides. Okay. There are also some other parameters here given for fire resistance. Up here we find all the settings that we have assigned to this member by the fire design configuration. And then we have some additional parameters here that I will focus on later. But for now, we can see, okay, for the cross-section checks, we have a drastic reduction of the resistance due to the increased temperature, which is very high in this case. Maybe we can also check the stability design check, because that also reveals some details to us. So first of all, we calculate the critical bending moment the same way as we do it for the code design. So I think this 757 should be the same for the code case as well. When we check the stability design check, yes, it is 1-to-1. But then in the fire situation, we have to again reduce it by taking into account a modified dimensionless slenderness. And in this case, this dimensionless slenderness is not only modified by the reduction factor for the yield stress, but also depends on the reduction factor of the stiffness, because of course stability design checks are also very much dependent on the stiffness of the system. So any degradation on that side will also alter our verification check for instability. Another important point is the derivation of our imperfection factor. While in the code case, this is dependent on the cross-section buckling curve. Here it is only dependent on the material of the section. So there are slight adjustments, but otherwise the schema for the verification checks is very similar to the code design case. I think we can agree that our first attempt to verify the fire resistance of this beam was not very successful. So yeah, what can we do to increase the fire resistance of our beam? Of course, we could lower the loads or increase the section size, but we have seen that the member heats up very quickly and we have only thus minimal strength and stiffness after 30 minutes. To discuss possible measures we can take to delay the heating process, I would like to come back to our formulas that describe the heat transfer from the ambient temperature into the structural element. So we've seen these before, and if we combine the two formulas, we get this quite long expression here. Most of the parameters represent physical constants that we as structural engineers cannot influence as much as we'd like to. There would be the specific heat of steel, the density of steel, the coefficient of heat transfer, the configuration factor, the emissivity of fire, and the Stefan-Boltzmann constant. Those we shouldn't touch at all. However, let's take a closer look to the expression AM by V. This ratio is also known as the profile factor and describes the ratio of the cross-section surface area to the volume per unit length or in other words, the profile circumference to the profile area in the section. So the profile circumference for the HEB 300 here would be the dashed red line, and the cross-section area or profile area would be the yellow section. If we now compare the three cross-sections shown here, so the HEA, a bit more slender than the HEB, and then the more compact section, HEM 300, we can see that the circumference of the profile hardly changes as the cross-section parts become thicker, while the cross-section area increases significantly. This means that more compact cross-sections have a lower profile factor, as demonstrated here in this example calculations, and as a consequence, and since the profile factor is in the numerator of this heating equation, compact sections heat up more slowly. And we will check this in a minute in the model again. But there are also other ways to reduce the profile factor. For example, if one side of my cross-section is protected from direct fire exposure, as shown here in the lower left figure, I can reduce the circumference by one flange width. So this could be relevant if we place a column next to a concrete wall or put a concrete slab above a steel girder without leveraging composite action. So such situation can also be considered in our program through the fire configuration settings. I will also show this later. Another factor that is influenced by the section choice is the correction factor for the shadowing effect. It is calculated from the profile factor for a fictitious box enclosing the cross-section, here shown in yellow for the I section, divided by the actual profile factor calculated based on the parameter of the section in red. For an I profile, I would, to calculate this, compare the length of the yellow line with the length of the profile parameter or the red line, and this would result in a correction factor of less than 1 because the yellow line is much shorter than the red line. This then, because the shadowing effect factor is also in the numerator, would again lead to slower heating. So I cannot activate this shading effect for hollow sections because, as we can see here on the lower right figure, the fictitious box aligns with the profile parameter. So let's note that branched profiles heat up more slowly as the thermal radiation cannot reach all areas of the cross-section equally well because there are some parts of the cross-section shadowing other parts of the section. Let's check if we can see or observe the described behavior also in our program by taking the appropriate settings. So let us switch to Rfem again, and I have also prepared a second model where I basically just copied my simple beam HEA 300 that we discussed before and changed the section into an HEB 300 and HEM, as I've also shown you as an example on the slides. And basically I applied the same loads and so on, and I conducted the fire design checks here. And it's of course no miracle that the utilization factor for the bigger profile HEM 300 is lower. This is expected when we choose a more capable section. HEM has a higher bending resistance and also much lower slenderness, which comes into play when we look into the lateral torsional buckling design check. But we don't want to focus on that, but on the member temperature and how it develops during the fire event. So we have already checked the temperature development for our HEA 300, and we've seen that at the end, at 30 minutes, we have 743.9 degrees Celsius. The HEB 300 is only a bit colder. It's 735.9, but when checking comparing this to the HEM, we see that by taking this much more compact section here, we get a lot less heating after 30 minutes. So the HEM only has a temperature of 628 degrees Celsius after 30 minutes, although unprotected. We said this is because of the profile factor, and we can check this profile or section factor here in the design details for all these members, and we can see that as we move on to the to member number 3, which is the HEM, we have a very low section factor, resulting in very low, or not very low, but lower temperatures. We also see the correction factor for the shadow effect that we talked about, also given in the design details. Okay, so we also talked about a second option to reduce or manipulate the profile or the section factor, and this would be by adding or avoiding all side exposure to the flames, for example, by a concrete slab. And I have also added another example where I modeled an HEB 300 and I modified the fire resistance configuration in that way that I only apply a 3-sided fire exposure. And as a result, we can see that compared to the standard fire case with 4-side exposure, it heats up like around 30 degrees Celsius less after 30 minutes, which isn't a huge deal, but it's something. And then last but not least, I wanted to show the influence of this correction factor for the shadowing effect. So I also incorporated a hollow section here, an RHS profile, which has a similar section factor as the HEB 300, but it doesn't profit from the shadowing effect. So let's go to the design details actually, where we can also see or check the KSH factor, and in this case this factor would be 1.0. So we couldn't leverage any of this here, and accordingly it would heat up a bit more even. Okay, that's about the section choice and how the section choice modifies or impedes the heating process of the member during the event of a fire. But there are actually there's actually another factor that we can manipulate and alter to adjust the heating process. So let's go back to the PowerPoint, to the next slide. Yeah, I would now like to discuss this factor here, epsilon m, which describes the surface emissivity of the member, not of the flame, but of the member. And this factor describes how large the proportion of absorbed radiation energy is. An ideal black body has an emissivity of 1 and absorbs all incoming radiation in theory. An ideal white body has an emissivity of 0 and reflects all radiation. Real surfaces have values between 0 and 1. Although this sounds highly theoretical, we are all very familiar with the relationship between surface emissivity and temperature development from real-life experience. So imagine on a sunny summer day, it is much nicer to wear a light-colored shirt than a dark one, as it reflects a greater proportion of solar radiation and does not heat up as much. That sounds good, but you might ask, what does that have to do with our steel member? And here we actually have the possibility to change the surface properties by galvanizing it. So as part of a research project at the Technical University of Munich, it was discovered that galvanized steel has a significantly lower emissivity than non-galvanized steel. We can leverage this effect at least up to a member temperature of 500 degrees Celsius, and only for shiny zinc coatings that we get for hot dipped galvanizing category A and B steels. if I am correctly informed, this additional regulation has already been included in the draft of the second generation Eurocode. In Germany, this option has already made it into the majority of state building regulations via an additional guideline published by the Institute for Hot Dipped Galvanization, named the Dust Guideline 027. So we can also take this galvanization into account in our program. I can show it to you. I think it's simpler. I show it to you just in the program. So just let's just jump back. And now I want to modify the selection of the members that I have modeled up front. So I again have copied all of those members that I've shown you before, different sections, and also the HEB with the three-sided exposure, and modified the fire design configuration in such a way that I also changed the emissivity by galvanizing the surface of the carbon steel. I can do that by just activating this option here, and then it actually also takes into account this limiting temperature of 500 degrees Celsius, and until then uses a lower surface emissivity. Okay, so let's see how this again affects the heating up of the member. We can see for HEA it does not have such a huge effect. Same goes for the HEB300. Let's actually look into one of those diagrams, because it reveals one important, or the fact that the emissivity changes at a temperature of 500 degrees. So as we can see here, there's a significant dent in this curve, and this is at a temperature of 500 degrees Celsius and marks the point where the emissivity jumps from 0.35 to 0.7. For the HEM profile, actually the influence of the galvanization is very, very huge. Instead of a temperature of 628 degrees Celsius, we get a temperature that is almost 150 degrees lower after 30 minutes. And that's mostly because for the whole time, for the whole 30 minutes, we are below a member temperature of 500 degrees Celsius, which means that we, until the end, can leverage from the lower emissivity of the member surface. And then, of course, the benefit is much greater, because it's more or less the integral of the heating over the time. But it is also interesting that, for example, when we consider an HEB300 and maybe anyway have one side of the section covered by, for example, a concrete wall or something, and we then take into account additionally the galvanization that we might anyway have because of corrosive protection measures, we see that we can reduce the member temperature from 736 degrees to 633, and we see that under this temperature we are even able to fulfill the verification checks, and instead of a maximum utilization of 200 something %, we go under 100. So without any additional measures in this case, we could already fulfill our fire verification checks. All right, last but not least, let us talk about conventional fire protection systems. Therefore, I would like to switch back to the PowerPoint presentation. So, as said earlier, the possibility to improve the fire resistance by galvanization is very interesting, as many steel structures are galvanized anyway for corrosion protection. But and in this case, the improved fire protection is a nice bonus. But conventional fire protection systems exist as well. They have a much higher protective value, and they can be also taken into account in our program. We can take into consideration spray, plaster, or board encasement, and such systems can be taken into account by using an alternative formula provided by the Eurocode 3 part 1.2 for the temperature development in internal steelwork that is insulated by fire protection material. In addition to some of the parameters that we have already introduced earlier, the properties of the fire protection system is also taken into account. So we have the thermal conductivity of fire protection systems, we have the thickness of the fire protection system, we have the specific heat and the density of the fire protection system. And also there's one specialty that we have to take into consideration when calculating the section factor, because it depends on whether I use spray plaster, which is applied on the perimeter of the section, or if I use board, which usually leads to a hollow encasement, and I have to calculate the section factor accordingly, either on the using the perimeter of the section or the hollow encasement or a fictitious encasement of this section as shown here on the lower right side of this figure. So those conventional fire protection systems can be easily considered in our program as well. So let's jump back into it and reveal the last member I modeled here. So in this case, again, I modeled an HEB 300 now with a 12.5 millimeter gypsum board encasement. Let's check what I've done to realize this. I go into the fire resistance settings, and there I just choose the fire protection parameters. I have a drop-down menu here where I can choose between the contour following or the hollow protection type, and then I just have to add the properties of my fire protection system based on literature or properties I get from the manufacturer of the fire protection system. And what I can see is that this has a dramatic effect on the temperature. So in this case, by the encasement, I get a very low temperature after 30 minutes, below 300 degrees Celsius. So higher fire resistance classes of R60 or R90 can also easily be realized with such sophisticated fire protection systems. Okay, we have now dealt extensively with the fire design assessment of a single member and checked how we can influence the temperature development in that member in the event of a fire. I would now like to move on and go to the more advanced topics and questions. One question I was occasionally asked before is, how do we consider the indirect actions due to thermal expansion in the analysis? So after all, steel wants to expand under increased temperature, and while in our last example the member was free to do so, in a real building like shown here on the lower right side, this is not always the case. However, such indirect actions from thermal expansion can be neglected as long as the simplified verification at member level is carried out with the standard temperature curve as describing the thermal action. I've summarized the relevant paragraphs of the Eurocode on the next slide. So let's check this out together. Okay. So in Eurocode 1, part 1.2, section 4.2, for 1, it is written that indirect actions from adjacent members should not be considered when fire safety requirements refer to members under standard fire conditions. And then there is also the clause in Eurocode 3, part 1.2, section 2.4.2, that the effects of thermal deformations resulting from thermal gradients across the cross-section shall be considered. The effects of axial or in-plane thermal expansion may be neglected, though. And because in the formulas that we use to determine the heating of our section always assumes that we have a constant heating over the section, we don't need to take into account the thermal deformations at all. However, there could be cases where you could be interested in determining indirect actions due to higher temperatures that must not always be under fire conditions, but could also be like if you have a compartment of a building that is heating up due to some chemical processing or because there's a heater in the room. So I want to demonstrate you how you could theoretically consider such analysis, such indirect action analysis in our software as well. Although I want to be clear again, in my opinion, you don't need to take this into consideration in the fire design check when following these rules that we discussed today. Okay, let's go back to the program and go into the third model I have prepared, which is basically the steel hall that you have seen on the slide before. In order to take the indirect actions or to calculate these indirect actions, we first need a temperature that we want to apply to this temperature. Sorry, to the model. And this temperature we could either derive by the standard temperature curve, or we could derive it by some other specification or a parametric fire curve, CFD analysis, whatever it is coming from. We need to have some make some assumption about to what degree our structure heats up. And then we can apply this temperature load via, for example, a member load. So I want to go ahead and create a new load case for this temperature load. And in this load case, I think it's sufficient to do it here. We want to analyze the effect of the thermal expansion. So I create a load case 10. Let's name it temperature. And in this load case, I want to apply, let's say we aim for a 30-minute fire under a standard temperature curve that would give us an ambient temperature of around 800 degrees Celsius. I have many sections here, of course, they would all heat up differently, but I will now just on the safe side and for demonstration purposes apply a uniform temperature change to all members of 800 degrees. So that's just some assumption. Okay, so I select all members and apply a constant temperature over the section, temperature increase. And now I could just run this analysis here, calculate the resulting reactions under this temperature increase. And I would be actually shocked because, as you can see here, we get very large restraining forces. So as I already mentioned, the steel wants to expand, and we have in this steel hall here bracings in some of these bays here, and the compression members between those braced bays, they cannot expand very much. So the thermal deformation actually goes into axial force, and we get a very huge compressive action here in these members. But now we have to consider one thing. Eurocode 3 part 1.2 says that we have to also modify our mechanical properties of the steel at elevated temperatures, and we can take this effect into consideration as well, because when we remember this diagrams we looked at regarding the properties under elevated temperatures, we may remember that we do not only decrease the strength of the material with increasing temperature, but also the stiffness. And the lower the stiffness, the lower these restraining indirect actions will actually be. So I have already prepared two materials. The first one that we just used for the first calculation step was just a regular mild steel S355, And the second one is a copy of that, but here I activated the user-defined material option and the temperature-dependent option. And by doing so, I am then allowed to enter a temperature-dependent modulus of elasticity, for example, and this curve is now just copied from Eurocode, basically. All these points are given in the Eurocode document, and we can leverage this to enter our temperature-dependent material properties. Also, I think the coefficient of thermal expansion is dependent on the temperature, and I can take this into account as well here. Now let's see what happens if we actually take this material into account, the temperature-dependent one, and how this affects the results, the indirect actions that are generated under elevated temperatures. So we remember we had in the first attempt compression forces of over 1 meganewton. Now we go into the simulation again with the temperature-dependent material. And let's wait a bit, but we should see that those compressive forces are very largely reduced. Yeah, we can see that it is almost reduced by a factor of 10. So now the compressive force that's left over at the temperature of over 800 degrees in the member is around 100 kilonewton compressive force. So whenever like talking about those effects or whenever we want to take these effects into account, we always have to remember that not only, okay, we have these restraints that add some actions into our model, but we also at the same time have the degradation of the material properties, which in this case help to lower these restraining forces in the model. Okay, so that's it for that question. Let's move on to the next one. How can we modify buckling length and boundary conditions for the fire design situation? Eurocode 3 Part 1.2 allows for reduction of buckling length in some specific cases. Such design situation dependent modifications of the buckling length can be taken into account with our construction stages add-on, and I want to quickly show you the necessary steps how to set this up. So let's go back to the program again. I don't want to go into a detailed explanation of the construction stages. There are some additional webinars that you could look into if you're interested, but just show you the procedure how can we modify the buckling length. So in this model, I think there are some buckling length for those columns here applied, for example, and we want to change them for the design, for the fire design case. So I activated the construction stages add-on, and I create a new construction stage where I want to activate basically all my objects that are relevant for my analysis. So all the members and nodal supports. I don't have any line supports or surface contacts or rigid links. And then under the member tab, I can not only activate or deactivate members here, but I can also modify them. And for example, I could now say, okay, this column here, for this column, I want to define some steel design configuration, for example, the effective length settings. And I could now override my original assignment of buckling length with a new one. Let's just take for demonstration purposes the type 2 I have already defined. But it could be every effective length type that I have maybe modified from the original version. Okay, I apply this with OK, and the thing I then need to do to assign this construction stage to my design situation 2 is that I need to apply all the load cases to this construction stage, and then in the design situation, or the easiest way to assign the construction stage to all load cases that are generated in design situation 2 is if I modify the combination wizard. So I will just, let's just copy the first one actually. And now in this case, we want to consider an initial state. And this initial state is defined as our construction state 1. I apply this with OK. And now let's see how those load cases look like. And I can see for all the generated load cases, construction stage 1 is now considered as being active. And that also means that the buckling length modification would be active. A second scenario would be that you may want to change a boundary condition for the stability checks, for example, or other stability checks. For example, in this case, when I want to leverage the rotational restraint of these girders in the code design case, I may wonder if, for example, if it comes from a trapezoidal sheeting, if I can, or if I should take this beneficial effect of the trapezoidal sheeting also into account in the fire design scenario, because if I imagine that there's a fire in this steel hall, these trapezoidal sheetings, they heat up very fast because they are very, very thin, just 1 or 2 millimeters. And as we learned, the material properties degrade very fast, and I wouldn't have a lot of stiffness that helps me in my lateral torsional buckling design check in the fire design situation. So if I want to be on the conservative side and don't want to use this beneficial factor in the fire design situation, I could also deactivate these line supports in that case. And that can be done via structure modification. I could assign the structure modification also to the combination wizard. That would be the most elegant way to have it active in all the load combinations that are then automatically generated. So I again open the combination wizard and now also in addition activate the structure modification. And in that structure modification, I want to deactivate specific objects. In that case, I want to deactivate the member support and to tell the program which member supports I want to neglect. I need to create this object selection. And here I can, for example, select the member supports by their number. And I can also select the member supports I want to deactivate graphically. I need to make them visible first. Here we go. And in this case, I would also take into account the structure modification. And again, all the generated load cases and load combinations, would have not only this construction stage where I modified the buckling length, but also the structure modification where I deactivated those rotational restraints here for the stability design of those girders. So I could do all of this. I am actually not sure in which cases I would do so, because the Eurocode also has a paragraph on how to define or how to take the boundary conditions into account in the fire design situation. And it actually says that the kinematic boundary conditions at supports and ends of members applicable at room temperature may be assumed to remain unchanged throughout the fire exposure. So this is just if you want to change something to be on the conservative side, you know how to do that. I have shown you now, and it's a bit engineering judgment if you want to modify those in the event of a fire. Okay, the third question considers the verification of steel joints. Of course, when thinking about a complete steel structure, we should not forget that we also have to verify the joints besides the members. And in Rfem 6, we have a dedicated add-on called steel joints for the verification of joints. But unfortunately, the design under fire conditions is not considered therein, at least not yet. But the experience shows from real fire events shows that joints are often not problematic. This is mainly due to the local mass concentration caused by welded-in sheets or stiffeners and bolts in that area. And the increased mass means that the joint usually heats up much less than the connected members. We have also significant shadowing because of these additional plates usually, which also affects the heating process. As a consequence, the Eurocode 3 Part 1.2 provides very simple rules for the verification of joints that you can leverage under elevated temperatures. And I think this is sufficient in many cases. So under section 4.2.1, it says that the verification of joints can be considered settled if the fire protection system used for the joint is equivalent or better than the fire protection system of the joint members. And the second condition is that the utilization of the joint should be lower than the utilization of all the joint members under normal temperature. So that means in best case scenario, we wouldn't even need to do a hot design for our joint. Alternatively, if these requirements are not fulfilled, we have Annex D to do a hot design of our weld or connection components, such as the welds and the bolts. And here again, we have to determine a temperature, and that can be based on the connected members. And here you can calculate this temperature by using our program, of course. And then with this temperature, you could derive the reduced capacities of bolts and welds and then verify your joint with those. The last question I want to tackle is how can I calculate the critical member temperature? This is also raised quite often. As I explained initially, the simplified member verification can be done resistance-based or temperature-based. And for now, we have only implemented the resistance-based approach since it is generally more economic and has a wider range of application. However, we are currently working on the implementation of this critical temperature calculation as well, as many customers are requesting this feature for their purpose. So I hope I can give you an update on this very, very soon. With this being said and looking on the clock, I would close the presentation and hand back the word to Andreas. Thanks a lot for your attention. I hope you learned something today. If you want to discuss something with me, feel free to reach out. And I hope we see each other in the next webinar. Bye-bye.
Thank you, Jonas, for your nice presentation. I have an additional hint. You can book our online courses. For example, Rfem 6. That's a course for beginners. Then the Eurocode 2 course for the reinforced concrete design with Rfem 6. Eurocode 3 for the steel design. You can get more information and the prices when you scan the QR codes in the middle, or you can click on the links at the bottom of the slides. You can download the slides from the same page where you can find the recording. You will get an email in the next days with a link to that page with the recording, the models, and the slides of today's webinar. That's a quite new course for Eurocode 5 for the timber design with Rfem 6, and also new are the course packages. This package includes the Eurocode courses, and this package also the Rfem 6 course. You have the chance to get the single courses for Rfem 6 or Eurocode 2, 3 or 5 for free. Just submit a customer project. You can also write me an email to info@dlubal.com, and I will answer you via email what I need for materials. It's not much work for you, I promise. Okay, that's also all from my side for today. I hope you enjoyed the webinar. Thank you for your attention. Thanks to my colleagues, Jonas for the presentation, Niklas for the help by answering the questions. I wish all a nice rest of the day. Bye-bye.